now it's when it's going to get complicated. Quickly, let's recap what I have in mind. So we've got the Wolfram model, right? We've got the Wolfram model, and this just so seems to try to map to path integral. Now, I don't like sure I know path integral sort of at the high level. I don't even know anything about quantum mechanics itself in terms of like I haven't really done anything like even with the Schrodinger's equation or anything like this. And so I want to try to understand better these mapping because, or at least the path integral, because one thing that I don't have clear about the Wolfram model is how entanglement in the Wolfram model, I just don't understand it, right? So, and because they're using the path integral stuff, so I thought maybe if I would figure out a way to, kind of do an exercise and sort of understand entanglement from a path with the path integral formalism, maybe that would help me understand a bit more how that maps to Wolfram's model because maybe this is just a different way, the reason it's modeled like that is because it's more similar to the path integral, right? Remember the ancestry kind of thing, right? So the fact that they say that the states are entangled if they share the same ancestor, so in the time evolution, and that's what I kind of have my mental model with the I'd say it's called the Hamiltonian kind of quantum mechanics or the non-path integral where you have operators and so you have your system and you have your states and then the entanglement is between the subsystems, right? Um, like you can talk about a state being entangled, right? But you're not rather talking about two. So you're talking about a state being entangled. You're talking about like the basis states having correlations, and then these kind of correlations is what then somewhat maps to entanglement, right? Like not all the basis state correlations are entanglement, some are, and so that's why. But maybe it's just the wrong way they name it. Maybe they just call it entanglement, but they just mean like correlations, right? So they just mean the correlations between the elements kind of stem from the ancestry from a time perspective, and they are not making any statement as in like that's entangled, right? Like as in like that's not separable. But I don't know. Let's see. At some point, I have to dig into this. I want to see if that helps me understand a bit more. And so, I kind of thought, what can we do? I mean, you know, I I think the whole quantum harmonic oscillator seems to be sort of the basic example that everyone goes to, or like the textbook example. And I thought maybe that will be something worth doing, right? To kind of go through maybe first the harmonic oscillator, the classical one, then go through the quantum one, see how can we do anything with it, how can we, so with the path integral, and then kind of evolve into more complex systems, then entangled systems. There seems to be an interesting, so this is what I found yesterday. There seems to be an interesting, or there seems to be something actually, like, for example, entanglement from path integral perspective. And maybe there's there is a relationship here because the path integral formalism is about like all the different paths that a system is following, and so maybe the entanglement it is somewhat defined as in like how are these paths branching, right? Space-time path integrals for entangled states. There is actually some research, but that's my guess is that's probably too complicated for me to even approach. So I want to kind of use the chance I said this whole new project is about learning quantum mechanics, so there's no better way to learn than to actually do the stuff rather than just read and then um, fool yourself that you kind of understand something. So we're going to spend the next video, it's going to be quite a lot, I guess, going through these, which I took I scanned quickly yesterday, and it seems to be the right type of level. There's a bit of there's some problems, some conceptual questions and problems, which we maybe can start reading these, because that sometimes helps with, then understanding what's the actual content about. So, kind of, my goal would be to go and, maybe several streams down from now, solve the conceptual questions and the problems, on stream, and then see. So I'll read them first and then kind of go. Just as I have absolutely no idea about any of these, right? I don't have any formal education on physics. I just, computer science. That's what I studied, and then did some basic physics, high school, and then of course university. But I haven't really done any of these. So let's see. What are the exercises? So it says, is it possible to measure energy of these for a quantum harmonic oscillator? Why not? Explain. No. Oh, but is it is it giving away the answers? Oh, come on. I don't want to see the answers. That's just spoiling the whole thing. Because I probably will not remember. What I should do is I should kind of maybe write them down and hide the answers, right? So explain the connection between Planck's hypothesis of energy quanta and the energies of quantum harmonic oscillator. That if a classical harmonic oscillator can be at rest, why can the quantum harmonic oscillator never be at rest? Does this violate Bohr's correspondence principle? Whatever that means. Use an example of quantum particle in a box or a quantum oscillator to explain the physical meaning of Bohr's correspondence principle. Can we simultaneously measure position and energy of a quantum oscillator? Why not? And problems show that the two lowest energy states of the simple harmonic oscillator satisfy this figure. If the so that's the, I hate it. I hate these. Why they don't want the solutions here? Come on. I might actually do other problems. Let's see. But let's go through the summary. I'm kind of reading this backwards because I think it's going to help me with kind of processing the details later. The quantum harmonic oscillator is a model built in analogy with the model of a classic harmonic oscillator. It models the behavior of many physical systems, such as molecular vibrations or wave packets in quantum optics. So I guess that's kind of, that's going to be the essence of this section. The allowed energies of a quantum oscillator are discrete and evenly spaced. The energy spacing is equal to Planck's energy quantum. The ground state energy is larger than zero. This means that unlike a classical oscillator, a quantum oscillator is never at rest, even at the bottom of the potential well, and undergoes quantum fluctuations. And the stationary states, I guess what this means is that the ground state is never classical in the sense that, like, there's no uncertainty about your position, for example, right? That it's quantum. So then just because it's quantum, the ground state is still kind of, in a way, there's still some uncertainty. So it's not that you can, find your position deterministically. It's probably where you kind of have the flatter, like a flatter wave function, I guess. But I don't know. The stationary states of definite energy, have non-zero values also in regions beyond classical turning points. Okay, so this seems to indicate that there's going to be a relationship between a turning point, which I guess the turning point is sort of if you think about, like, I think the typical classical harmonic oscillator is like a thing on a spring, and then I guess the turning points are where it kind of stops and then springs back, with the spring being maximally like stretched, and then it goes and it's maximally compressed. And so I think those are the turning points. And so what this is saying is maybe, because those are the points of highest energy. These are the points where if you think about energy, the energy of the system as being sort of the the kinetic plus the potential, and I guess the potential here will be related to the springiness or spring constant of it. I guess those are the moments where the kinetic energy is kind of zero, right? Because you're not, like, for an instant you're not moving. So somewhat these turning points map to the definite energy states. Least likely position for a classical oscillator. So when in a ground state, a quantum oscillator is most likely to be found around the position of the minimum of potential well at the ground state, which is least likely position for a classical oscillator. I mean, for a classical oscillator, where is the spot with the less energy? I don't know. For high quantum numbers, the notion of a quantum oscillator becomes more similar to the notion of a classical oscillator in accordance with Bohr's correspondence principle. For high quantum numbers, what are high quantum numbers? What are quantum numbers? To complete describe an electron and atom, 4 quantum numbers are needed: energy, angular momentum, magnetic momentum, and spin. The first quantum number describes, I don't know if these are those, but like, okay, so I guess what this is saying is that at a larger scales, then these approximates a classical oscillator, which is what you would expect probably. Okay, let's get started. The quantum harmonic oscillator. So by the end of this section, you'll be able to describe the model of the quantum harmonic oscillator, identify differences between the classical and the quantum models of the harmonic oscillator, explain physical situations where the classical and the quantum model coincide. And I'm gonna go deep in the sense that, like, I mean, I don't know what's the best way to approach these, like whether just kind of scan through and then kind of go back to, probably that's what I'll do, and I'll come back to the points where I don't know, how to unpack, and then we kind of will unpack them in the subsequent or coming up streams. So oscillations are found throughout nature in such things as electromagnetic waves, vibrating molecules, and general back and forth sway of a tree branch. In previous chapters, we used Newtonian mechanics to study macroscopic oscillations such as a block on a spring and a simple pendulum. In this chapter, we begin to study oscillating systems using quantum mechanics. We begin with a review of the classic harmonic oscillator. That's why I picked this, because I saw that it starts with an overview of the classic one, which, to be honest, I think it's worth a refresh. A simple harmonic oscillator is a particle or system that undergoes harmonic motion about an equilibrium position, such as an object with mass vibrating on a spring. In this section, we consider oscillations in one dimension only. Suppose a mass moves back and forth along the x direction about the equilibrium position. So the equilibrium, okay, it's said to be x equals 0. In classical mechanics, the particle moves in response to a linear restoring force. And I guess this k is the spring constant, or the sort of, yeah. So this is a force that depends on the position, and this constant that is somewhat related to the spring, right? So this means, kind of course, I guess that's something that's constant, but then the farther away you're from the center, so the higher your position is, or even in negative terms, if we assume that you can kind of spring both ways, right? And this is x0. In negative terms, the absolute value of the force will still be like the highest, the farther the farther you are from the equilibrium position. Where x is the displacement of the particle, from the equilibrium position, the motion takes place between two turning points, x equals a, where a denotes the amplitude of the motion. The position of the object varies periodically in time with angular frequency. Okay, I don't know. I wouldn't know how to calculate that, though. How to arrive at that, which depends on the mass m of the oscillator and on the force constant k of the net force and can be written as, okay, so there's a function that is a cosine function, so it's kind of going to look like wavy, and that basically describes the position. Yeah, I don't know, I don't remember how you derive the angular frequency. And why is it even a square root? Sure, it will depend on the mass. The heavier the object, sort of the slower it will move. If you think about angular frequency as in like, if we're trying to think about like, the whole thing spinning rather than just moving like these, the bigger the object, the slower the movement will be. So I assume that, okay, maybe, yeah, that's something you can derive through speed, but we can work that out later. So let's just go through everything, but that kind of makes sense in a way. The total energy of an oscillator is the sum of its kinetic energy and the elastic potential energy of the force U of X, which is, I guess those are given definitions. I really don't know how do you derive the kinetic energy, even classically, right? It's one of these things. It's directly proportional to the mass of the object and to the square of its velocity. I don't know. Something to unpack later as well, maybe. So you have the energy described like these. Oh, what is U here, though? Huh? Is U velocity? At turning points A, the speed of the oscillator is 0. Therefore, at this point, the energy of the oscillation is solely in the form of potential energy. The plot of the potential energy of the oscillator versus its position is a parabola. The potential energy function is a quadratic function of x measured with respect to the equilibrium position on the same graph. We also plot the total energy of the oscillator as a horizontal line that intercepts the parabola at x equals a. Then the kinetic energy, K, is represented as the vertical distance between the line of total energy and the potential energy parabola. Okay, there's a lot to unpack here, I guess, but I think I'm following so far. So the potential energy, well, of classical harmonic oscillator, the motion is confined between x equals a. I guess there's a minus missing here, and x equals plus a. The energy of oscillations is, I mean, that sort of makes sense. So if this is the potential energy, right? This is a total energy. Yeah, so actually, in the ideal case where there's no other forces, no friction, no nothing, then you kind of expect the total energy to be conserved in this case, right? So here you have at minus a and plus a, you have no speed, so you have no kinetic energy, but you have the maximum potential energy. And as you move closer to the center, your potential energy is decreasing, but then your speed is increasing, and so your kinetic energy is increasing. And so at this point, the equilibrium point, you kind of only have kinetic energy, or almost only, right? I guess it's approaching 0. But I think that's the idea. In this plot, the motion of classical oscillator is confined in the region where the kinetic energy is non-negative, which is what the energy relation says. Physically, it means that a classical oscillator can never be found beyond its turning points. Yeah, so you'll never go beyond these A's, right? Okay, but I get it that probably in the quantum case, if you were to map these points as in like definite energy points, like let's say you would map minus a, and 0 as sort of the definite energy points where one of the components of the energy is 0. I don't know, I'm just making this up, right? But I guess that would make sense, or that could make sense. Like in the quantum case, you'll still have some quantumness to it, and so you will, you might be able to just measure the position even beyond these, right? It means the constant can never go beyond the turning point. Its energy depends only on how far the turning points are from its equilibrium position. The energy of a classical oscillator changes in a continuous way. The lowest energy that a classical oscillator may have is 0, which corresponds to the position where the object is at rest. And it can only be at rest in the equilibrium position, of course, because otherwise it's going to have some k and some force. It's going to have, like, because there's a displacement and there's a constant k, then there's going to have a force. And so if there's a force, then it means there's movement, and so it means there's speed, so there's kinetic energy. So, the energy is not 0. The zero energy state of a classical simply means no oscillations and no motion at all. A classical particle sitting at the bottom of the potential well. And I guess this figure. When an object oscillates, no matter how big or small the energy may be, it spends the longest time near the turning points because this is where it slows down and reverses its direction of motion. Therefore, the probability of finding a classical oscillator between the turning points is highest near the turning points and lowest at the equilibrium position. Okay, so note that this is not a statement of preference of the object to go to lower energy. It is a statement about how quickly the object moves through the various regions. It makes sense. Here it slows down, and then it sort of moves back also at the similar speed, just inverted, right? So that kind of makes sense that it spends more time in these regions than in this region where it just goes like, it passes fast and both ways, and he just slows down. So time in this case is, of course, then related to the displacement and so the velocity and the displacement and how fast you're moving across multiple regions. So okay, so that's about it for the classical one. I think that's fairly okay. I mean, sure, I don't know how to. I don't really remember how these things are derived, and maybe I can come back to this later. But it's like okay, so this model makes sense. Of course, it's ideal, but let's get into the quantum stuff. So one problem with the classical formulation is that it is not general. We cannot use it, for example, to describe vibrations of diatomic molecules, where quantum effects are important. A first step towards a quantum formulation is to use the classical expression k equals mw2 squared, which I don't know what this means. So is w the angular momentum? And m the mass? To limit mention of a spring constant between the atoms. In this way, the potential energy function can be written in a more general form. Okay. What does this mean? That we imagine there's a spring between atoms, or there's springs between atoms. What are these? What are diatomic molecules? I guess they are molecules that have two atoms at the core or something like that. I guess this di, it's usually for two in Latin or Greek or whatever. Of only two atoms. There you go. Okay, cool. Yeah, okay, so that's easy in the sense that it's a simpler model because you can define the spring in between the two articles, and so we know these vibrate and yeah. We're quantum effects. Okay, so classical expression to limit mention of a spring constant between the atoms. But the potential energy. No, give me a second. I'll be back in a second. There we are again, delivery. So, where was I? The potential energy stuff, right? So, kinetic energy, blah, blah, blah. Where's the potential energy? So, yeah, so there's this defined as this constant, right? Okay, so the only thing that we do here is okay, I think what they're doing, but I don't know where this is coming from, is saying, okay, that's how you would define K. That's how, I don't know what W is though here, but that's how you would define K when you're defining a spring between the two particles or the two atoms. Okay. Because it's then something probably that it's, I'm assuming the mass of the atoms is the same, or there's a total mass, I don't know. And I don't know what W is though. But I guess that's the point of this. And then, okay, so now now that gets interesting. So combining the expression with the time-independent Schrodinger equation. So this is okay. So this is the biggest. This is the first biggest blocking point for me, right? So how? Okay, so the time-independent Schrodinger equation. So this this is probably going to be the next step, right? So hyperphysics. Not time dependent, I want time independent. Time independent. Okay, so the time independent, it just says these, that predicts that the wave function can form standing waves called stationary states. These states are particularly important as their individual study later simplifies the task of solving the time-dependent Schrodinger equation for any state. Stationary states can also be described by a simpler form of the Schrodinger equation, the time-independent Schrodinger equation, where E is the energy of the system. This is only used when the Hamiltonian itself is not dependent on time explicitly. However, even in this case, the total wave function still has a time dependency. In the language of linear algebra, the equation is an eigenvalue equation. Therefore, the wave function is an eigenfunction of the Hamiltonian operator with corresponding eigenvalues E. Boom. Yeah, okay, but that's all that's saying is that you have a state and then you multiply and then this energy operator. Okay, so that's this part here, right? Because remember that's, I guess that's what we're trying to find is the energies. Okay, so what we're saying is we know, or we kind of know how the Hamiltonian looks like, or at least we can formulate that because we know these. We know this because of what? Eh, It's potential. What is all this shit here? So this is the potential energy, and this is going to be what, the kinetic energy? But that's already something that is the derivative, blah, blah, blah. So that's already something that's expanded from that definition, isn't it? Oh yeah, that's so here there's the Planck constant stuff, but then there's 2m, and this is the second derivative of x, or of the wave function with respect to x, which is what we're trying to measure, right? So what is the kinetic energy classically? Is 1/2 times m times u squared, and u is the velocity, I think we're saying, right? So the velocity is, but the velocity is the first derivative, right, of position. Oh, sorry, where was I? And here we've got, I don't know if that's the second derivative or the square of the first derivative. And here is 1/2, but then instead of mass, it's the Planck constant or the reduced Planck constant divided by m. I don't know where is that coming from. This with respect to time. We're doing it with respect to position. Okay. Okay. So what is these? So introduce of physics or chemistry to introduce question in a way that can be appreciated knowing only the concepts and notations of basic calculus, particularly derivatives with respect to space and time. A special case of an equation that it needs a statement in those terms is the position space Schrödinger equation for a single non-relativistic particle in one dimension. And I guess that's our case. Oh, look at this. Here's where we have it. So okay, so this is the part. Yeah. So this part here is the one that's in here exactly. Cool. So here psi is a wave function, a function that assigns a complex number to each point x at each time t. The parameter m is the mass of the particle, and v of xt is the potential. Why this keeps the people use this stuff, whatever. So that's the potential that represents the environment in which the particle exists. So okay. The constant I is the imaginary unit, and h bar is the reduced Planck constant, which has the units of action, energy multiplied by time. But what does these represent then? What is this thing here? I guess that all between the brackets is the energy. So that's, in a way, the kinetic energy, isn't it? Which is a function of the displacement, which kind of makes sense. Hmm. Yeah, okay, but that's the energy stuff. What's confusing me is, oh yeah, okay, so that's the energy stuff. Yeah. Cool. I don't fully understand that, but okay, so it's something plus the potential energy, and that's kind of what we've reformulated in here. And okay, so but what is it that then solving for? To solve this figure, that is to find the allowed energies. Okay, so that's what we're solving for is the energies and their corresponding wave functions. We require, the thing is, I feel I don't really truly appreciate the Schrödinger equation. I don't really truly appreciate what it's telling me. I don't know. The corresponding wave functions, we require the wave functions to be symmetric about x, the bottom of the potential well, and to be normalizable. These conditions ensure that the probability density must be finite when integrated over the entire range of x from minus infinity to plus infinity. How to solve is the subject of more advanced course in quantum mechanics. Here we simply cite the results. Okay, but that's so. So the result is this function, right? Where you have this n, which are kind of, I guess, how do you even get there? Like, how do that would be okay. So that's probably going to be the next thing. Is like, how do we solve these? But I still don't fully appreciate what this is. It seems to be that this has got to be the kinetic energy in a way, because it's a constant that multiplies a derivative of position, right? Which is velocity, right? Which is in the classical case what's happening here. This u is a velocity, I think. But so that's the result you get. And so you kind of you plug this in here and you have like the energy levels, or you have a function that describes how the wave function that corresponds to the wave functions that correspond to these energies. Okay, so these are valid values in here, and then you can have, if you plug them into the Schrodinger equation, then you can solve for the wave function. And so what it will tell you is at each energy level, how is the wave function looking like? The wave function, then remember, this is what's kind of supposed to help us then. It's what describes the position, or it's what describes the state, right? So you can query that wave function to get the position, to get the momentum, to get all these kind of different properties. But it's the wave function is what describes the system. It's just at different energy levels, the system is described differently. And that's what you can find through the Schrodinger equation. The wave function corresponds to these energies are these. And so you have the wave functions. And so beta is blah, blah, blah. It's a normalization constant, and Hn is polynomial of degree n called the Hermite polynomial. The first four Hermite polynomials are, what the fuck? I have no idea what this is. That is actually probably complicated to derive. A few sample wave functions are given in figure. Oh, there you go. So at each, yeah, okay. Okay. So at each energy level, you have a different wave function, and that's sort of an example, right? Where here you have the highest probability is that it's found in x equals 0. With n equal 1, then you kind of have the highest probability. A bit, a bit towards the right, a bit towards the left, even if it's negative, right? That's still absolutely, it's still indicating that there's a higher probability because these are complex numbers at the end of the day. Oh, okay. Interesting. Interesting. As the value of the principal number increases, the solutions alternate between even functions and odd functions about x equals 0. The first 5 wave functions of quantum harmonic oscillator, the classical limits of the oscillator motion are indicated by vertical lines. Okay. Correspond to classical turning points at x equals a of classical particle with the same energy as the energy of a quantum oscillator. Okay. So that's to say, if the energy of my classical system would be n2, then this will be a, this will be a, right? But then you can see that in the quantum case, it can be found most probably here, here, and in the middle. Okay. So classical region of harmonic oscillators, find the, oh, sorry, I'll delivery. Be back in a second. So, how much time we've got left? Not much, to be honest. Sucks. Okay, anyway, classical region of harmonic oscillations. Find the amplitude A of oscillations for a classical oscillator with energy equal to the energy of quantum. Blah, blah, blah. Wait a second. The classical region of harmonic oscillations. Find the amplitude A of oscillations for a classical oscillator with energy equal. Strategy. There's something wrong with the formatting here. I feel like that's just a title and then it's just it's kind of an exercise. Find the amplitude A of oscillations for a classical oscillator with energy equal to the energy of a quantum oscillator in the quantum state n. The strategy to determine the amplitude A, we set the classical energy equal to En given by yeah, you set the energy, then you kind of like derive all the other ones. So we can also do that. Solution we obtained blah blah blah, and so we obtained these and significance as the quantum number n increases the energy of the oscillator, and therefore the amplitude of oscillations increases. For fixed natural angular frequency, for large n, the amplitude is approximately proportional to the square root of the quantum number. For large n, the amplitude is approximately proportional to the square root of the amplitude number. Several interesting features appear in this solution. Unlike a classical oscillator, the measured energies of quantum oscillator can have only energy values given by the figure. Where does this even go? It doesn't even work. Moreover, unlike the case for a quantum particle in a box, the allowable energy levels are evenly spaced. When a particle bound to such a system makes a transition from a higher energy state to a low energy state, the smallest energy quantum carried by the emitted photon is necessarily HF. I don't know where I take that from, but similarly, when the particle makes a transition from a low energy to a high energy state, the smallest energy quantum that can be absorbed by the particle is HF. A quantum oscillator can absorb or emit energy only in multiples of this smallest energy quantum. This is consistent with Planck's hypothesis of the energy exchanges between radiation and cavity walls and the black body radiation problem. So there's another problem here. Vibrational energies of the hydrogen chloride molecule, the HCl diatomic molecule, consists of one chlorine atom and one hydrogen atom. Because the chlorine atom is 35 times more massive than the hydrogen atom, the vibrations of the HCl molecule can be well approximated by assuming that the chloride atom is motionless and the hydrogen atom performs harmonic oscillations due to an elastic molecular force modeled by Hooke's law. The infrared vibration spectrum measure what is the spacing between the original. Okay, so we can do that exercise. We can do that exercise as the next thing in the next. So what is the force constant K of the atomic bond in the HCl molecule? How should I go about doing these exercises? Like, do I do by hand, or do I just use like something like NumPy and Python to help me with the yeah, probably. Spacing between the vibrational energies of this molecule. But that will involve solving the Schrodinger equation, wouldn't it? Wouldn't that involve this? Checking the standing. What is the force constant of the molecular bond between the hydrogen and the iodine atoms? Okay, so some problems in here. First, the ground state of a quantum oscillator. Not zero in the classical view, the lowest energy is zero. The non-existence of a zero energy state is common for quantum mechanical systems because of omnipresent fluctuations that are a consequence of the Heisenberg constant principle. If a quantum particle sat motionless in the bottom, it would be exact. So it would violate the uncertainty principle. Yeah. With non-zero probability outside of these intervals, in the classic formulation of the problem, the particle would not have any energy in this region. The probability of finding a ground state quantum particle in the classically forbidden region is about 16%. Okay. For a quantum oscillator, the ground low energy state is largest in the middle of the well. For the particle to be found with greatest probability at the center of the well, we expect that the particle spends most time there as it oscillates. This is the opposite to behave with the classical oscillator, in which the particle spends most of the time it's in the turning point. Okay. Check your understanding. Find the expectation value of the position of 4 particle in the ground state of harmonic oscillator using symmetry. X equals 0. Okay, that's a solution. I hate this. Is there something like quantum harmonic exercises? Oh, there's some stuff in here. Yeah, we could use these. Oh, that's actually a German university. Consider a one-dimensional quantum harmonic oscillator described by Hamiltonian. Oh, so they give the Hamiltonian already, but that's kinetic plus potential. Canonical commutation relation. I don't know what the hell that means. Write Hamiltonian with respect to dimensionless position Q and momentum P operators defined as follows. I have no idea. That's way above. Okay, so we should probably stick to these problems first. Okay, so I see. That's what happens probably when you know increase n, and so your distributions start getting a bit more like they actually look like the potential well of the classical case. Which kind of makes sense because it then seems to indicate that that's kind of like the idea that as energies grow, or as you go bigger in scale, then you get into the classical regime, which is what we see, which is kind of that's what we observe, right? Yeah. But okay, so and then there's a summary I already read, and then there's some conceptual questions. Is it possible to measure energy of for a quantum Harmonic oscillator? No, yeah, okay, that's yeah, okay. So I'd like to know a bit more about how to solve these. I know that it's probably way above my pay grade, but I'd love to see how these solutions are found. Quantum harmonic oscillator. So that's the Schrodinger equation, because that's still sort of the Hamiltonian way, right? But I'm like I at the end of the day I'll be interested in how the path integral version of it looks like. So that kind of will be the next step, I'd say. But let's first try to go through these. So in the next session, and I guess I'm going to leave it here. In the next session, I'm going to be diving into the how is that derived? How a bit more the actual Schrodinger equation. Let's put it this way. I'll just maybe take that example and see how can we get the quantum harmonic oscillator solutions. And how do you know that n must be an integer? Like that's for me that's what's interesting. So how do you get to the fact that this must be an integer? And then kind of what are the spacings of energies? I guess will be the energy between n0 and n1. Like that's always going to be, but like that's kind of what That's the biggest unknown component of the whole thing. Is like, how do you go from, from these? And conceptually, let's kind of start, go back a little bit, just recap. So you have you have in a classical system, you have energies. These energies are functions of position, of velocities, of whatever, right? And so this means that if you know the energy of a system, you can pretty much know and derive, like, how it's moving and how fast it's moving and stuff like that. That's kind of like what you can see here in the model, right? Now, what the quantum analog of these is saying is that the ways things move are specified in the Schrödinger equation, right? Which is, basically, yeah, sure, fine. But like, oh, this one here, right? So I is the imaginary number, is the Planck's constant. So in classical, you have kinetic plus potential, that's the energy. And so there's the conservation of energy. In quantum, you have, okay, so basically, in quantum, the energy is the Hamiltonian operator. The energy is then described by the Hamiltonian operator, which is conservation of energy, Schrödinger equation. So this is momentum, or what is that? In making the transition to a wave function, physical variables take the form of operators, right? So say the position is an operator, it's the position operator. Um, yeah, I gotta dissect that a little bit more. Maybe I'll just almost actually wanna, yeah, but it's essentially the same. Kinetic energy and potential energy. It's just that you just have these constants in here. Yeah. Yeah, but that's basically, it's the same. It's so classic. It's telling you, like, look, that's the energy is kinetic energy plus potential energy. It's just that the way you describe kinetic energy and potential energy is essentially different, because now you must define them as operators. Because why? Because the way you define a state is not by just a given instantiation of variables, but it's by a wave function. And so position is an operator, in a way that if it kind of tells you how the position is evolving. God. So yeah, that's why this is defined this way. So essentially, the Schrödinger equation, yeah, it's these, right? So you have potential energy, and then times the wave function. Then you have the these stuff in here, which is the kinetic energy, which it will be interesting to know where it comes from as well, because that's definitely something that is a function of velocity. But then again, for these, maybe I should also understand how these are classically derived, because I think they're inspired, or they seem to be really similar, right? At least it's the same constant, like a half. So this is a half of the mass times velocity squared. That's the kinetic energy. So that could be something. So where's the kinetic energy coming from, classically, and how do we translate that? How do we translate that to that portion of the Schrödinger equation? that's kind of that's one thing, of course. Just it bothers me not knowing that. But then how to solve that? It's probably just a technicality, right? So how do you solve these types of equations, which is basically, with derivatives and stuff like that. And how do you get to that result? Anyway, that's for the next stream. Um, but I get it. You got a good overview. So let's see. Let's see. Bye bye.